Okay, so today we're going to do a few things which aren't covered in DeBurg. And the problem we're going to be looking at mainly today is something called the closest pair problem. So this is an example of something which is often called a proximity or a nearest neighbor type problem, sort of the easiest of all of these, right? The basic idea is pretty simple. We're going to just say, given some set of points P, right, contained in RD, find a pair Pi, Pj in P, where they're not equal, and the distance between Pi and Pj is less than or equal to the distance between any other pair of points. So we'll say it's basically the min of all KL of Pk minus PL. So maybe we have like a bunch of dots here, and say like these two happen to be the closest pair of dots. So we want to report this closest pair. This could have a number of different applications. For example, maybe you have some kind of physics simulation or something like that, and you always want to find the closest pair of particles, compute some interaction, and then maybe update them, kick them apart or whatever, and then advance the simulation some time step. So that could be like one thing that you would use this for. But our main interest here is going to be somewhat academic, because we're going to use this as a motivation for looking at some other sort of geometric problems in the same vein. And for reference, we already know how to solve this problem in 2D, right? So we can just use a Delaunay triangulation. So we'll say in 2D, the Delaunay triangulation gives an order n log n solution without much trouble. That obviously doesn't work in 3D because we run into quadratic territory, and then at that point we might as well have just brute forced this problem, right? So the brute force solution for this is just order n squared, and that would be the same as what we would get with a Delaunay triangulation in 3D. So that would be kind of stupid.
Can't you also just do that divide and conquer solution for 2D?
There are multiple ways to do it in 2D, but we're not going to worry about 2D today. We're going to be looking at general cases. So there are many algorithms for solving this in 2D, right? You could do it with a Delaunay triangulation. You can do it by divide and conquer. You can do it with a sweep line. Many solutions, but we're going to be looking at it in general, right? Right. There's also a lower bound here, too. So in the decision tree model, so this is basically a model of computation that only counts the number of times you have to compare two elements. And so your operations are you can compare things, swap them, whatever. The lower bound on this is omega n log n. Right, so that's the. So that would seem to suggest then that n log n is tight. You can't do much better than that in general, right? The way in which you get this reduction, and I won't prove it in detail, right, but I'll just sketch it out, is that you can reduce this problem of finding the closest pair of points to detecting a duplicate, right? And the problem of detecting a duplicate in the decision tree model is omega n log n. I mean, because basically if the closest pair of points are basically zero distance apart, then you have a duplicate in your array, right? So that's the idea. So that's the lower bound, omega n log n. But today we're going to show how you can smash this, and you can do it in order n. So today, order n. How do we do that? Well, obviously we don't work in the decision tree model, right? We're going to go to some different model of computation, which will allow us to do things much faster. Specifically, we're going to work in and actually an extremely powerful model of computation, which is a kind of augmented real RAM model. So let me write that down. So today's model of computation, it's actually so powerful it's almost absurd. And I will kind of sketch out why that's the case. But the things that we'll do today won't be too unreasonable, right? So today's model. Today, we're going to work in a special real RAM computer with 3 extra properties, or 3 extra features. So the first of these is we're going to allow for a random number generator. So we'll allow for calls to rand or whatever, some sort of pseudo-random generator. That's reasonable, I think. I mean, we've already kind of done some randomized stuff before, so allowing randomness doesn't seem so bad. The second thing is we're going to allow for hashing, right? So we'll have arrays with constant time access. So we'll basically say we're going to use hashing. Again, not so unreasonable, right? I mean, that's basically how in the word RAM model you can do sorting in order n instead of order n log n. So no big deal. And the last one, and the seemingly innocuous one, is we're going to allow for a floor function. This is basically like round an integer down. So we'll say round x to like the smallest integer below it. Equivalently, you could also use like a threshold function, or we could call it round, just like a proper round function, whatever. There are many sort of equivalently powerful things. OK? So of all of these 3, the one which seems like it's maybe the weakest one, right, is we got this extra floor function. So what good is taking a floor? It turns out that this actually is the most powerful function, right, in this entire list of parameters, which we've added onto the real model. And in fact, it interacts with the real model in some extremely chaotic and bizarre ways. So here is a sort of theorem, right, which is basically real RAM plus a floor function solves p-space hard problems in order n to the k, right? So basically, like the real RAM model, if you just stick in a floor function, allows you to solve any problem in p-space. And for clarification, p-space is orders of magnitude more hard than NP hard problems would be, right? So any problem in p-space is equivalent to something which you can get by simulating a Turing machine with a finite amount of memory, right? Or a polynomial amount of memory. So the fact that you can do these sorts of things in the real RAM model with this floor function kind of tells you that once you throw this thing in there, a lot of lower bounds just go out the window, right? Now, the way in which you prove this is actually kind of horrible, right? It involves basically like taking the state of your entire Turing machine that you're simulating and then packing it into a giant like real number and then reading out the values using this floor, right? It turns out without the floor, you can't read those values out, and so the simulation doesn't appear to be possible. But if you add in this floor function, then all of a sudden real RAM, even with just rational like circuits otherwise, right, becomes extremely powerful and actually unreasonably so, right? So today, we're not going to do anything so perverse as that, so we won't have to worry about this fact that this model of computation is like extremely chaotic and broken. But it's something to keep in mind, right? That really, like, this is not a great theoretical way to sort of do geometry, right? I mean, once you throw these functions into the picture. But the stuff that we will do today, though, will actually be valid in a sort of ordinary word RAM computer where our real numbers would be represented by floats. Right, so the things that we're going to look at aren't like really like hideously broken, insane pathological constructions. So that's just to kind of set the stage for where we're going to be. All right, so okay. So the first way that we're going to look at solving this closest pair problem using this model is using a really simple idea called a grid. So grids are kind of the hashing analog for geometric problems. And you can solve a lot of things with grids. pretty fast, right? So here's the basic idea for how grids work, is that we're going to take our points here, and then we're going to imagine chopping space up into boxes. Then we're going to just take each point and figure out which box happens to contain it, and then just snap it to the grid point associated to this box. So each of these things would just like snap down here, 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 etc. Well, you have to add another row. You get the idea, right? So the snapping process we can define given some parameter, which is going to be the radius of this grid. So in this picture here, the dimension of one of these boxes is going to be r. It'll be this parameter that we'll use that will control the size of the grid. And so our rounding map here, we're going to call this thing g sub r, which will take a point in the real space here, right, which would be like our ordinary coordinate system where our points live, and then we're going to just snap them down to this grid z to the d, right? So if we take this grid point here and we feed it in some values like, say, x, y, z, etc., then this is going to be equal to this real vector x over r, y over r, etc. Right? So we basically just take the components of this vector, divide them by the size of our grid here, which is r, right? And then round them down using the floor function. So we'll call this space z of d, right? This is the integers, raised to the dth power. So it's the Cartesian product of the integers d times, right? This is the grid, right? Right. And we can think of, instead of storing this grid as some dense array, right, you could imagine storing it as a hash table, right? So we'll suppose that maybe if we want to store entries that are basically keyed by these integer coordinates in the grid, then we can basically do some sort of sparse data structure, which allows for constant time access of this grid, right? So we'll basically assume, basically maps of the form z to the d to whatever, some other type s, can be maintained in order 1 update or query time, and order, the size of the number of entries in this map space. So we have some compact, efficient way to represent these things, right? Which practically you would get with a hash table. So that's the basic assumption. So far, so reasonable, I would say, right? So OK, how do we use this now to do closest pair detection? So that's actually a little bit tricky, but we're going to start out with something very, very simple, right? So the simple version of this is we want to detect if the closest pair is within some distance. So we're going to call this closest pair bounds, right? This is some function which will take a point set as input, right? And it's also going to take another parameter, r. And this will basically return one of 3 possible values, right? It will return -1 if the closest pair distance is less than r. It'll return 0 if this is equal to r. And it'll return +1 if it's greater than r. So we'll just think of this as like a sort of comparison function, right, where we can basically say, OK, I guess what the distance is, say it's some value r, and then I want to basically test in, say, order n time, right, whether or not it's bigger than or less than that, right? And so if we had such a function, we could actually, in the number of bits of precision in r, do a binary search to find it, right? That would be one hypothetical way we could do it. But we'll see later how you could do it somewhat faster. But this is the simple idea, right? So we can use this to very quickly, bound the radius, right, of the closest pair. OK, so how do we do this? I'm going to erase this picture here. and we'll write it out. The algorithm is very simple, and it's sort of typical for how like a lot of grid algorithms work. The basic idea, though, is that we're just going to take all of the points and then stick them in a grid of radius r. And we will use this to detect if 2 points happen to be within some distance of one another of order r. Right? So here's the idea. So we'll call this, keeping with the same name as before, closest pair bounds. Take our point set P and our radius r that we're querying. We're going to initialize our grid with some empty hash table. So we'll basically set the grid to an empty hash set, right? Whatever. So this is just an empty hash table. And we're going to define this parameter here, rmin, right, which is our current best guess at the minimum radius, to infinity. All right? Now we're going to march through all the points. So we're going to say for p sub I in P. And the first thing we'll do is we'll round this thing down to its corresponding grid point at the radius r. Right? So this will basically take our parameter r here and P, and it will give us our rounded down quantized point value. All right, so we snap it to a grid cell. And then we're going to compute a neighborhood around z sub I, which I will basically write in the following way. Right? So we're going to say that this is basically I'll call this function cluster, right, of z sub I. How does cluster work? Right? Well, actually, let's have this function take the grid as input and z sub I. Right? So we'll say cluster does the following. We're going to take our grid, and we're going to have some query point z. And then what this is going to do is look at all of the adjacent cells to z. Right? So this will just do something like, say, for d0 equals -1 to 1, stepping by 1, for d1 equals -1 to 1, etc. Right? I mean, you can think of this as just counting base 3, right? And so the sort of geometric picture here is that we have our grid, right? We have our query cell here. We're going to loop over all of these neighbors here. So we're going to loop over this neighbor, this neighbor, this neighbor, this neighbor, this neighbor, this neighbor, this neighbor. So this will be 3 to the d neighbor cells, right? And then I guess we should probably return some result here. So we'll set the result equal to an empty array. And then we'll just say result is basically the result concatenated with whatever was in the grid at z plus this vector d0, d1, etc. Right? So you see, it's kind of a little hairy to do this, right? But if you just think of this as like a couple of loops, then it's not so bad, right? So when we're all done, we just return the result. That's it. I mean, all we're doing is we're just saying, OK, we take the point, loop over all of the adjacent grid cells. If that grid cell is empty or is filled, then we take all of the points which are stored in that grid cell and return it. Right. So here's the idea. And so now here's the next step. So we'll say for p sub j in n. So now these are all of the points which are in all of the grid cells adjacent to z sub I, right? We'll set r min to the min of r min and the distance between pi and pj. I guess I'll write it like this. And we'll say if r min is less than r, we will return -1, right? Because we've actually found a certificate that the closest pair of points is definitely less than r. Otherwise, we'll go take the grid point at zi, and then we're going to append p sub I to that grid cell. So we're going to basically take them and stick them in the list. Then after the loop is finished, we'll say if r min equals r, return 0. Otherwise, return 1. So I claim that this will actually run in order n time, completely deterministic, no matter what inputs you give me, right? And so how do we prove that this is true, right? There's no assumptions about the input here, right? We're not making any kind of like randomized or ad hoc thing, right? This is, not at the randomized stage of this yet.
Wouldn't the n squared if you make the radius huge?
No. I will show you what happens, right? So there are basically two cases here, all right? The first case is that we have one of these two scenarios, or we have this scenario, right, where r is definitely bigger than this, okay? If that's the case, then every time we get to one of these loops over here, we're never going to find a neighbor. So basically, each of these buckets can never have more than, say, 3 to the d points inside them, right? So the first case here is, let's consider each case. So the first one is that the minimum radius is greater than r. Well, this implies no bucket has more than 3 to the d points, right? Well, that's like, okay, easy, right? Because that means that every time we're inserting them in there, we're just inserting into like tiny lists, so it's no big deal, right? So whenever we go through this inner loop, it's never going to become too large, right? So that's good. Pretty much ditto for the case where r min equals 0, except we have to consider the sort of pathological case, right? So the question then becomes, how many of these points can we stick in a single grid cell before it overflows, right? So to do this, I'm going to now have to draw a picture somewhere. I think I'm going to erase this little chunk down here because this is kind of trivial, right? This cluster function. So here's sort of the idea. So imagine I have some grid cell. Maybe it's in 3D, 2D, however you want to draw it. The situation is analogous. I want to fill this thing up with as many possible points, right, so that it doesn't overflow. Well, here's a simple kind of scheme, right? I guarantee that I can never put at least more than this many points inside there, because otherwise it's going to blow up. Which is I can put 1 point here, 1 point here, 1 point here, subdivide the face, right? Subdivide the interior. So basically just put 3 to the d points in this box. Each of them, right, if their radius happens to be touching, right, so the radius of each of these sides happens to be one sphere here, this will completely cover the box, right? So there's sort of an upper bound with the number of points that I can put into this box. It's definitely smaller than 3 to the d. So I know that if I've ever packed more than 3 to the d points into one of these boxes, then there has to be a pair inside them whose distance is less than r, right? And so if that's the case, I would detect it here, return -1, and I would be done. So the case where r min is less than 0 is handled, right? We will definitely detect it, and we'll basically return early in this case. And then, so in the case where r min equals 0, we'll basically loop through this whole thing. We won't have found any collisions, and then at that point, we will be done, right? That's the key argument, is that we'll never be able to basically fill this thing up. Because if we did fill it up, then r min would be less than r, and then this loop would terminate. That's the reason that this works, right?
So sorry, how big are the grids? Because I thought
these are each
dimension was r.
Right. This is a dimension of r. This is a dimension of r. So if I took 2 points and put them on the line segment next to each other here, then these would be exactly a distance of r apart, right? But I could put them on, like, say, the opposite vertices of the cube, and then they would be like basically r times square root of 3 or square root of 2 or whatever apart, all right? But I can never fill this thing up completely with these like little spheres, right?
So couldn't you not put one in the middle like you have it?
Yeah, well, you would put the one in the middle, right? I'm just saying that this is sort of like an over-dense packing, right? I mean, I'm just saying that you can never put 3 to the d of these points inside the cube, right? If you put more than that, it'll basically overflow, and I will have caught it, right? So the key thing is this, right? Is that this is basically small, right? I mean, because d is going to be small. If I treat d as a constant, it's a constant, right? That means that the size of each of these buckets is only going to be at most constant, right? And therefore, I can just keep looping through this, and if one of them ever does happen to overflow, then I will have actually detected a minimum which is smaller than r, and the loop will terminate. OK, So this is an order n deterministic algorithm. And it uses the magical power of the floor function, right, which is like a very dangerous and unholy object in computational geometry that you must be very careful with. So, all right, that's the simple algorithm for computing the bounds. All right. So now we're going to modify this a little bit, and we'll use it to actually find the closest pair of points. So, all right, I'm going to just erase this whole thing. All right, so the basic idea for the full closest pair algorithm is pretty similar to this, all right? But it relies on randomization to locate the closest pair. So this is where we'll end up making a randomized argument. All right. Whatever, I don't need this. OK. All right. Let's now walk through this for a point set P. So I'll write this in a somewhat higher level way, right? It's actually a little bit nastier to do this full function, but it's not horrible. All right. So here is the basic idea, which is that we first shuffle the points, right? So this is typical for most randomized geometric algorithms. The reason we'll have to shuffle them will become apparent. OK. So the way I want to say this is, so I'll write it in steps like this. So this is a sort of pseudocode description. So after we've shuffled them, we're going to start inserting these points into a grid, right? Or actually, no, let's write it like this. So we'll basically define this parameter r, right, which is going to be the distance between the first 2 points inside this array, right? So we'll basically initialize r to a guess, right? So we're going to guess that just it happened to be that after we shuffled the points, the closest pair were the first 2 in the array. All right? OK. Now, basically, we'll say for each point p2 all the way up to pn minus 1. So basically, for the next set of points, insert into a grid. Right? So we're going to basically start inserting them into the grid. And so if at pi, right, the closest point so far to pi, right, is closer than r, then we just rebuild the whole thing. Rebuild grid. So we basically rerun the whole insertion. So we basically just say, like, go to 3, right? So we just blow the whole thing up and rebuild it, all right? So this is kind of the high-level thing. And then when we're all done, return closest pair. All right. So this is a little bit messier than the last time, right? I'm sorry for that. But let's just walk through what's going on here, right? So we basically are going to be starting out with the same sort of story as last time, right? So we have a bunch of points. We're inserting them into the grid. And then basically we have a similar type of condition where at some point we're going to insert a point into the grid. And then it's going to turn out that this point that we're inserting into the grid happens to be closer to some other point in the grid than the points that we've looked at so far, right? So one way that we can think about this is up until iteration I of this loop, we have at least verified that the closest pair of points is greater than, or is less than or equal to r, right? So the sort of loop invariant that we have is that at iteration I, closest pair distance is greater than, or is less than or equal to r. All right, that's the first point to realize, right? So we should be relatively convinced about that. And so in a sense, when we're basically sticking the ith point into the array, what we're really doing is we're just testing if the closest pair distance to this ith point is going to be less than or equal to the closest pair distance that we found so far, which is the current resolution of our grid. So we take this point pi, we stick it in the grid, right? And then we just check if we found a point that's closer to pi. If we do, then we can say, OK, well, that point and pi are our current best candidate for the closest pair. Then we can take that new radius, blow up the whole grid, and then rebuild it. All right? OK, so this seems like it could be kind of bad, right? Like, what happens if we keep on inserting the points? So imagine, if we gave it points which were something like this, right? So maybe the first 2 points are distance 1/2, then the next 2 are 1/4, right? Then the next one is 1/8, and so on, right? So that's sort of like logarithmic, or 1/2 to the k decreasing. So that would be pretty bad. The way that we hedge against that, though, is that we're shuffling, right? So the idea is that each time we insert a new point into the array, the probability that we're going to have to rebuild should be relatively small or bounded, right? So let's try to think about how big that probability will really be if we actually do the shuffle. Well, we're only going to have to do the rebuild if this pi and the previous point over here are the closest pair. So this is the next key point. Say only rebuild if p sub I is in closest pair of p0 up to pi, right? So in other words, if we take this whole subarray, right, we're just saying that if we happen to randomly choose this latest point that we pick, what is the probability that this thing happens to be one of the closest pair, right, inside this array of points so far? Well, there's only 2 out of n points inside here. So the probability that this thing happens to be one of the closest pair of points in this array is 2 over I, which is basically, another way of saying this is that this is basically a probability of doing this rebuild. I'll write it this way. So I'll say probability of rebuild is equal to 2 over I. All right, that's the key, right? So let's now calculate this, right? So the total cost of running this thing, right, or the expected cost, we'll write this as basically E of t, is going to be 1, right? Well, that's basically because we have to initialize this whole thing, plus the sum from, say, I equals 2 to n of 1 plus p of rebuild times the cost of rebuilding all of the things so far, which is order I, right? So that's basically an I operation. So if we do this, this probability of a rebuild is equal to 2 over I, right? So we get something that looks like 1, pulling out the 1 over here, right, which gives us n, right? So it's 1 plus, we'll just write it this way. We'll say order n plus the sum from I equal 2 to n of 2 over I times I, which actually this would just be an n over here, right? So I didn't even really need the order n. Whatever. So it'll be basically n plus the sum of 2 over I times I, which is equal to 3n. It's a little kind of messy on the whiteboard, right? So the expected number of times that we're going to have to loop over every element in the array, if we do this shuffle first, right, so assuming that we're just getting them in some completely random order, is going to be 3n, right? So this algorithm, the total expected time is order n. And it uses order n space, right, because we have to store the hash table. So, OK, that's an example of what you can do with grids. So with grids, we've now seen that we can basically beat that n log n lower bound, all right, and get it down to an order n algorithm for finding the closest pair of points. OK. Any questions about that so far?
So if you wanted to use d as part of the runtime.
Yeah, OK, yeah, I forgot, right. Yeah, times, well, there's basically this exponential number of neighbors that you have to search whenever we're looking for this nearby point. So that's actually the place where d comes in, right? Forgot to mention that. So yeah, d does play an important role. The issue is that when we do this search for the closest pair of points, we have to search over all of the neighbors there. That's going to be on the order of 3 to the d, or 2 to the d, depending how you do it. So it'll be n times 3 to the d. So it'll be pretty expensive in dimension, but that's fine, right? We're not going to worry about this factor today, because d is going to be like, say, 3, 4, 5, something like that, right? If you're doing some sort of machine learning type thing where you want to find something in d equal like 100 or whatever, then this is not a good idea. But for geometry problems, like finding a bunch of points in some mesh or something like that, finding the closest pair, this is a good way to do it, right? So that's the concept, right? Another place where this actually turns out to be pretty useful, though, is that oftentimes if you do want to build a grid for some point set, you usually want to basically make the radius of your grid or the size of your buckets relatively small, like on the order of the closest pair distance. So you can usually use something like this as a pre-processing step to just warm up your subsequent use of the grid, right? So this is not necessarily a rigorous theoretical kind of idea, but it's something that you often would want to do in practice. So that's where closest pair calculations become somewhat important, is that if you are going to then use the grid for some other thing, you would like to figure out how big to pick R, right? And this is a good criteria for selecting R. OK. Right. So there are a couple of other things you can do with grids. They're not as algorithmically sophisticated as this, but they're still very useful, and it's good to keep it in mind. Right. So one where they show up very, very frequently is in particle simulations. So here's kind of the picture. So this is not for the closest pair problem. This is just a general application of grids. So actually, I'll just erase this whole thing. All right. So we'll say grids for particles. So so here's kind of the idea, is suppose you have a physical simulation where you have a bunch of these particles, which are going to be represented by disks of some fixed radius, right? So each of these things has like the same radius r, whatever, right? And so we'll basically say given n particles represented by balls with radius r. Right, so this is sort of the idea. So we have a bunch of these like little particles. They're all kind of like moving around, bumping into one another. So maybe they like hit, bounce off, right? So what we would like to do, right, is say, OK, given all of these particles, in this system, moving around, bouncing and interacting with each other, report all of the particles which happen to be overlapping, right? So we'll assume that for the most part, these particles are all disjoint. Their centers don't really touch. But then occasionally they come into contact, and then we have to resolve that contact in some way, right? So and I drew them as like sort of like rigid particles, right? But sometimes these could also come up as like, say, like nodes in some sort of smooth particle hydrodynamic simulation. So these could be like little Gaussian bumps, right? And then maybe we just chop it off so that it goes to 0 outside of some radius, right? So we have like these like little sort of like flat spline functions. We just want to figure out when they overlap. And then if they overlap, we'll be calculating some energy potential or restitution force that then tells us how the system has to separate them. So the geometric problem, though, is just find all pairs of overlapping disks. This problem happens to show up all the time in computer graphics, right? So for lots of geometric simulations, you would like to do this, right? OK. So anyone want to take a guess as to how you solve this thing, right? No, it's simpler than that. You just stick them all in a grid, right? That's it. You literally just stick them in a grid, look for collisions. That's it. So how to do this? Answer, stick them in a grid. That's it. That's all you do. You just take these points, right? You just chop it up into space, stick them in a grid of radius r. That's it, right? It's exactly the same thing that we did, right? There's like almost nothing going on here. You just stick them in a grid. If two things overlap, then you just have to check their neighbors, right? So if we have two particles that overlap here, we just check the neighbors on all of the sides. That's it, right? So really, really simple. The complexity of doing this is order n plus the number of overlaps, right? So the complexity is going to be order n with some factor of d, right? So I should actually write it, say like n times 2 to the d or 3 to the d. It doesn't matter. It's some constant to the d plus k, right?
Wouldn't the number of overlapping be dominated by n?
It might not. I mean, we can just charge the overlapping, right? Because sometimes we might have like extra junk sitting around in a cell. So we want to basically deal with that case. The way we do it is we just stick that in the k term here, right? So that's the idea, right? I mean, it's pretty simple. It's like, OK, you just march over them all, stick them in a grid, check the collisions, done, right? So this is like the good enough for like 99% of the time collision detection algorithm, especially when you have lots of particles. One slight refinement over this is that this time complexity is optimal in the sense that it's, if we ignore the d factor here, right, it's basically order n, right? So you can't get much better than that. But the one sort of drawback here is that this is sort of a very rough analysis, right? So this would basically be optimal in the word RAM model, in word RAM or real RAM. For a fixed d, right? The thing is that sometimes, or in the real world, right? The real world is actually a little more complicated than just the word RAM because you also have caches involved, right? So in the real world, this may not actually be necessarily the best way to do it because every time we're inserting one of these things into this grid over here, we have to do a completely new lookup in the grid, from scratch, right? Which is, OK, it's constant time, but all of these subsequent accesses, for each of these particles is going to be completely uncorrelated. So the time complexity would be order n, and it won't scale with memory bandwidth, right? So the problem is that sort of not cache efficient, and it just doesn't scale with block size, right? So it will. Have you guys heard of a concept called like a 2-level memory model or I/O memory model, right? So it doesn't scale with block size. So there are lots of things that are kind of in a similar vein, right? I mean, this is sort of analogous to this problem of detecting duplicates in an array, right? If you want to detect duplicates in an array, you can use hashing to detect those duplicates in basically order n time. But the problem is that that duplicate detection will not scale with cache, right? You're not going to get this sort of block size speed up. So in practice, even though it has a worse performance in the word RAM model, the better way to actually do this is to actually just sort them, right? So the simpler answer, the more practical answer, or the one which is actually faster in the word RAM model. So faster or the one that's faster in the cache, in an I/O model. Sort the points. So this is the one which you would use if you were implementing this on a GPU or doing some kind of like crazy like high performance parallel version of this thing, right? Or if you have like like millions and millions of points, and you want to get like the very highest possible performance, what you do is you take each of your particles, you round it down to a grid cell, you sort that list of all of those integer coordinates, and then detect overlaps in that sorted list. The cost of doing that is bounded by the cost of sorting, which runs in order n over b log bn, where b equals size of your of cache line or block or whatever. So typically, if b is bigger than log b n, this is a net win, right? Net win over hashing, right? So I haven't explained the I/O memory model here, but maybe you've already seen this in some other course, right? I mean, it's, I think these days, somewhat of a standard thing. I don't want to go into it right now. OK, so suffice to say, sorting is better. The one somewhat tricky thing with sorting, though, is that when we're detecting these overlaps, we need to actually look at these adjacent cells, right? So there's a slight trick when we're scanning the sorted list, right? So we can use this to detect if two things happen to hash to the same cell, which is great, right? But we would also like to detect, we also need to search over the neighbors, right? So the way you do that when you use this sorting method is that you basically walk a set of pointers over the sorted array, right? So the way you do this is, if we sort this list, right, this is basically like taking all of these grid cells, and then we're going to like lay these out here, and then kind of walk through here. Right? So we basically are just sort of walking over this thing in lexicographic order. All right? So this is basically sorting. Right? When we lay them out in like lexicographic order in this array. And so what we can do is that as we're marching through the array, right, we keep track of our current cell here, and then we'll also look at the cell directly below it. And then when we walk to the next entry in our sorted array with this thing, we also march this pointer forward 1. And so we just march these two pointers forward constantly. So this pointer, every time we take one step, this pointer has to take one step, and so on. So we just keep track of, we can imagine that we like have like our little frontier of grid cells. We just move them lockstep through all of these arrays, right? One after another as we keep cycling through the grid cells. That will basically take, this scan operation will take order n over b times 2 to the d time, right? And we have to maintain 2 to the d pointers when we're doing it. So that's the sort of like high performance, particle collision detection application of grids, right? Where you see them often, right? So like a lot of GPU-based collision detection algorithms do this, essentially, right? So you have like a bunch of particles, all pretty much the same size, calculate their interactions by sorting them. OK, so that's one place where we see them. Another related operation to this, right, and it's actually not a big change, is we have a bunch of points which are, say, relatively uniformly distributed, and we want to find all points for any query point which are within a given radius. So this is sort of like a, an R nearest neighbor query. So we can also do these R nearest neighbor queries, which is, find all points in P contained in a disk of size R. Again, we just do the same thing, right? We basically hash them to a grid. For our query point, we just do a lookup inside the grid, check the neighbors of the query point. Now we've got all of the particles or whatever that happen to be within radius R. As far as I know, for most 3D applications, this is actually what people tend to use, right? So there's actually a system called near point 3, right? This is the fastest sort of practical industrial grade 3D closest point algorithm. There are problems with this, though, right? So one issue is that this will only pull out the r nearest neighbors, right? But it'll do it in constant time, right? So this is like really fast for pulling them out if you happen to have like points which are all relatively clumped together, which happens to happen a lot in like most sort of industrial applications, right? You're not sampling from some uniform distribution. You have things which are all kind of grouped. And for points that are far away, you don't even care about them, right? So you only want to get the ones in the r radius. So for those, this is a fantastic solution. But if you have a more general question where you want to say, like, find the closest point in the worst case, where maybe it's like extremely far away from my query point, then this turns out to be like extremely inefficient, right? Because it could have to search through every single point in the data set. So this is great when you only want the points within a fixed radius, right? It's actually pretty garbage if you just want general 3D closest point queries, right? So it doesn't work for those. But in practice, you may not care about them, right? Maybe this is enough. So this is a very common and fast solution for this closest point problem for 3 dimensions, right? At higher dimensions, you use very different types of solutions. So, OK.
Can you use grids to do just nearest neighbor in general?
I don't know of a good way to do it, actually. I've never seen such a thing that really works for nearest neighbor in general. So I don't know. There are ways to do nearest neighbor in general, but they don't involve grids. Right? And actually, in high dimensions, most of them get really crazy. So they all kind of involve approximations of some sort. So OK. So I think that's all I'm going to say about grids for today. I don't have much time left, so I'm going to just start talking about a second concept, and I'll show how you can use it to solve the closest point problem again. It won't get in an order n time, but it'll get an order n log n time. And it'll turn out to have some nice kind of applications when we move on to some other types of things. So this will also like generalize into a bunch of other like nice things, right? But we're going to start out just looking at a way to solve this closest point query problem. And this one won't use the floor function or hashing or whatever, or any kind of like randomization if you're morally opposed to such things. So this is a simple deterministic algorithm for getting an order n log n closest pair of points. Right. Right. So let's go back to the closest pair of points again. And this technique is actually much more general than for finding the closest pair of points, right? It's actually a really neat idea called a well-separated pair decomposition. Yeah, and so the idea behind a well-separated pair decomposition is that it takes some collection of points, and instead of finding all interactions, all n squared of them, it computes a summary of these interactions, which is only order n. So the idea is to summarize the order n squared interactions between all pairs of points in P. So we basically take any pair of points in P. We'll think of that as like one of these interacting pairs. And the way we'll construct this summary is that we're going to group them into clusters. So we're going to say by grouping points into clusters, which have this property, which are well separated. All right, so this is the high-level idea. So we're going to say that, OK, we have like a bunch of these points here, maybe these other points over here. So what we'll do is we'll cluster these 2 points together. And then we're just going to store the interaction between the 2 clusters in this data structure. So that's the idea. So we're basically going to have this set of pairs of clusters. Each cluster will act like a pseudo-point. The total number of clusters will be about order n. All right? And so this is sort of like our all pair interaction summary. Right? And it turns out that once you have this decomposition of a set of points, there's a ton of stuff that you can do with it. Right? The very least of which is closest pair of points. But I don't know if we will get to it today, because I think we only have like 20 minutes left or something. So we may have to finish this up on Tuesday. So OK, what do these clusters look like? Or what do these sort of pairings look like? So the idea is that each of these clusters is going to have this property, which is that they are well separated. OK? So to do this, we're going to define a concept called a well-separated pair. And actually, I'm going to add a parameter in here. So we'll call it a well S-separated pair. The idea is we'll say let A, B be two point sets in RD. All right. Define, first of all, the diameter of one of these point sets A, which is equal to the radius of A's bounding sphere, right? So supposing that this was set A, this was set B, this radius here, that's the diameter of A. Similarly, over here, this is the diameter of B. OK, so far so good. Right. And similarly, we're going to define the distance between A and B, which is the distance between their bounding spheres. Right? So this is the distance between, you have to be slightly careful here. I'm going to call largest bounding sphere. That's not the right way to write this. OK, the idea is that we're going to suppose that we have bounded them both by a sphere of the same radius. So suppose that A is bounded by a sphere of radius diameter A, then we better suppose that B is bounded by a sphere of radius B. So that is, another way to say this is that we'll basically require that this bounding sphere that we picked for both of them is the same, right? These spheres don't have to be tight, by the way. They just have to bound the point set in some way, right? It'll turn out that if you make it tighter, it'll still work, right? It's just we want them to be the same size for now. So we'll require that, in this case, the bounding sphere for A is equal to the diameter of the bounding sphere for B. All right? So now here's the punchline, right? So they're well separated. If and only if the following is true, which is that the distance between them is greater than or equal to S times this diameter of A, right? Or whatever, or diameter of B. So the concept is that if these spheres were very large, then they would have to be very, very far apart. Or if they were very tiny spheres, then we could push them much closer together, right? But they have to be at least S times this distance apart between the two of them. So that basically this length here, right, we'll call this R. R has to be bigger than S times the diameter of the larger of these two. All right, so you take whichever was bigger, that's the diameter that we're going to force them to be separated by. Right? I mean, instead of requiring them to be equal, I could set this equal to the max of the two diameters. It's just they have to be pushed far apart, right? So they better be like really, really far away. OK. So that's the high-level idea. Now, one consequence of this is that having this kind of bound puts some bounds or constraints on where these points can be distributed within these clusters relative to one another. So specifically, if I take a point here, P, right, inside A, and another point here, Q. Let's call this radius here d of PQ, right? Then it turns out that for any other point, say I pick another point here, I'll call it P prime. Call this one P prime. Maybe select another point here, call it Q prime. Then knowing the length of P to Q gives me a lot of information about the length from P prime to Q prime, right? Given that these pairs are well separated. Specifically, we can say the following, right? Which is that if I take the distance from P to P prime, right, this better be less than or equal to 2 times the diameter of A, right? Shoot, how am I doing for time here? No, OK, I'm good. And ditto for the other one, right? So we take Q minus Q prime. This better be less than or equal to 2 times the diameter of A as well, right? Because A and B, we're putting them to the same diameter in this case. All right. And moreover, right, if I use the triangle inequality, then I know that the distance from P prime to Q prime, this has to be less than or equal to the distance from P prime to P plus the distance from P to Q plus the distance from Q to Q prime, right? So that means that the distance from P prime to Q prime is less than or equal to, if I kind of draw this out here, this distance from P prime to P plus this distance from P to Q, so walking along that edge, plus this distance, right? This is just, basic geometry. So it's the triangle inequality here, Q minus Q prime. All right. And I also know that the distance between P and Q, right, better be bigger than or equal to S times the diameter of A, right? So this whole thing has to be less than or equal to 1 plus, if I divide the S over here on both sides, right, then this becomes d of PQ is greater than or equal to the diameter of A. So these are all less than or equal to, so that means that this quantity here is less than or equal to 2 over S times P minus Q, right? The distance over there, ditto for this, 2 over S, P minus Q, right? And so this whole thing reduces down to 1 plus 4 over S, P minus Q. Right. So what this basically tells us is that if I take any points over here, and I know that these two sets are S separated, then the distance between any pair of points here or any other pair of points inside this cluster is at most 1 plus 4 over S, right? If I pick S equal to 4, then there's actually at most 2 times that other parameter, right? So it's now at most a constant times it or something. So that's the idea. OK, so that's what it means for a pair to be well separated. It's a pretty strict requirement. So what is a well-separated pair decomposition for a point set? Well, it's basically a complete decomposition of all of the pairs of points into well-separated clusters, which has the following properties. So let me write this out. Where do I want to do this? OK. OK, so a well-separated pair decomposition, which I'm going to write as WSPD, right? This is basically a collection of well-separated pairs, we're going to call them as A sub I, B sub I, such that for any distinct PQ in P, there exists some pair. We'll, again, I guess just call it A sub I, B sub I. So there's some big set of pairs, right? So we have like a collection of these things where basically P is in A, I, and Q is in BI. So that is that, every pair of the original set of interacting points, right, is represented by some, well-separated pair inside this decomposition, right? So if I take any, if I take any pair of points, I can always find some well-separated pair in this decomposition that splits them apart in some way, right? Okay, so if we combine this definition, right, with this thing that I just erased here, unfortunately, it tells us one important thing, right, which is like almost an immediate consequence about the closest pair of points. So we'll say the closest pair PQ is in the WSPD. So that is, if I take that point, there better be some entry inside these things that looks like PQ. Well, why is that? Well, basically, suppose that one of these things was not a singleton, right? So that there were multiple points inside that well-separated pair decomposition. Well, I know that the radius of that thing, right, is going to be bounded in a sense by the distance between P and Q. So what will end up happening, right, is that basically Q would also have to be contained inside that pair. But that violates this condition that I can always find a distinct pair that separates any pair of points. So therefore, the closest pair of points is represented in this well-separated pair decomposition exactly, right? And by a similar argument, you can actually show that every point inside this set is also represented by some well-separated pair that contains that point as one singleton set, right, inside this well-separated pair decomposition. So that's rather remarkable, right, I guess. I mean, there are trivial ways that you can build such a well-separated pair decomposition, right? So, the fact that one of these things exists shouldn't be too striking, because I could actually just take every pair of points, right, and then construct a well-separated pair decomposition, right? So the trivial well-separated pair decomposition is I take all pairs and then construct this whole mess from them, all right? However, it turns out that you can build well-separated pair decompositions of size order n. So this is the really interesting thing. So this is the more useful theorem, which is that there exist well-separated pair decompositions of size order s to the d n. So basically, this parameter s here determines the size of the pair or this well-separated pair decomposition, and it's exponential in the dimension, but for 2 or 3D, who cares, right? Actually, I forgot to say one thing, right? This is only in the well-separated pair decomposition if s is greater than 4, right? Or s is greater than or equal to 4. I forgot that. Yeah, it's a slight technicality, right? But in order for that inequality to actually hold, you need this s greater than or equal to 4. OK. OK, I don't have tons of time here. So this tells us that we can get the closest pair of points in a well-separated pair decomposition. And if we can build these things fast, which we won't see how to do today, but we'll see how to do later, then you can use this to get the closest pair of points relatively fast. In fact, it will turn out, right? So later, we will see how you can construct these things pretty quickly. All right, so the time complexity will be s to the d n log n plus s to the d n. All right, so that means that basically in n log n time, you can find one of these well-separated pair decompositions for whatever crazy point set you throw in. So that's the kind of neat application for all of this. Now, there's more that you can do with these things than just find the closest pair of points. I'm just going to go through and summarize all of this stuff right now. Right? I'm not going to go through it in detail yet. We will see it Tuesday. OK, so here are sort of a laundry list of applications for this. Right, so the first is that in addition to finding the closest pair of points with this well-separated pair decomposition, we can do the following. So we'll say applications of this thing. Right, so why it's important. So the first one is we can do closest pair in order n log n, ignoring the dimensional constant, right? 2, we can find the k closest pairs. So not just the single closest pair of points, but the first k of them in order of n log n plus n times k, right, where k is the number of pairs that you have to report. 3, we can find all closest pairs. So this is a little bit trickier, right? It's not the same thing as the k closest pairs, because we could have duplicates of the same point showing up in there. This is just, i.e., for every point, find closest point. This is not a symmetric relationship, by the way. So maybe I have something like this, where I have 3 points here. These 2 points would be closest, but then this one might be closer to that one than the other one, right? So this is basically like a map from every point to the adjacent point inside the set. We can do this using the well-separated pair decomposition in n log n, which is pretty awesome, right? I don't know of any other kind of nice ways to do that. So those are kind of the sort of direct, easy to verify things. It also turns out to be very useful in a variety of geometric approximation algorithms. So this can be used to construct a spanner, right, which is basically a graph that approximates the distances in the point set. So we can construct approximate spanners. Okay. Similarly for Euclidean minimum spanning tree. And you can also approximate the diameter of a point set. All of these, again, basically order n log n, right, which is kind of neat. A more exciting application, though, is you can also use these for multi-body dynamics. And this is actually where this turns out to be the most important. So we can actually use it for approximate n-body simulation. I'm going to say a little bit more about that right now. So just how this works, what you do with it. Actually, I only have a minute left. But I'm just going to talk about this last point here. So how you do this one. OK. High-level idea. These are sometimes called fast multipole methods. Right? So they're basically techniques that you can use to speed up the interactions in huge systems of particles. So in a normal sort of n-body problem, you have a bunch of these points, right? Then each of these points interacts with every other point by some force, usually an inverse square law, right? So we have some huge collection of points. So n-body problem. We have n points, each interact with some inverse square force, something like that, right? So we have some force. It falls off as 1 over r squared. So very distant points don't do a whole lot, but nearby points interact very strongly. OK. So the idea is that we basically approximate cluster forces, usually using some sort of like function fitting or interpolation method, typically spherical harmonics, right? So typically as spherical harmonics. So we can kind of compute some effective force that like a cluster would have. So imagine we have like a huge number of points out here. We can just wrap that up in a cluster and then pretend that it was just a single particle, right, that has some force that it exerts. And then we basically only integrate forces between clusters. So we basically construct this well-separated pair decomposition. For every cluster in this decomposition, we calculate an effective force, which will be some good approximation of the forces that this thing would exert. And then because these things are sufficiently far apart, we can then calculate all of the interactions by, instead of doing like n choose 2 or n times m different interactions, we just do n plus m interactions for each of these clusters. And so that ends up reducing. So the concept is that it basically reduces time from order n squared to order n. It's only an approximation, though, right? So it's only going to work if these things really behave as clusters. But that this works and that this is a reasonable thing to do is sort of a physically motivated idea. If you have, like, for example, like a solar system with like a bunch of planets in there and they're all interacting through gravity, you don't have to like simulate that thing at like the level of individual molecules. You can imagine grouping all of those molecules up into like planets or asteroids or something like that. Then you approximate that thing as like some sort of point mass in a higher order system, right? And you can just keep on iterating this process over and over again until you can now just look at only these interactions between these cluster bodies. And then those will be very small. Like the number of interactions you need to represent is only order n, not order n squared. So that's the idea. So this basically, or actually it's n log n because you have to build the well-separated pair decomposition, which I haven't talked about yet, but we'll see later. OK, so I think that's it for today. Any final questions? No? All right.